presentation here. So these are the three areas that we're going to be concentrating on here. So we need to design for strength, we need to design for life, and we need to design for vibration. So the initial design that we're going to be applying is that we want to make sure that the stress developed in the system is below 150 megapascals. We want to make sure that the frequency that the fatigue developed in the system, that we can make sure that it is able to last for 1 million load cycles, which is the equivalent of 10 to 20 rallies. And finally, we want to make sure that we avoid the frequency, any natural frequencies in the system, between 1 and 30 hertz. So this is our overall assembly that we're looking at here, but what we want to focus on is a subset of this assembly. So I'm going to focus that. I've got a configuration here that only includes the components that I want to work on. Excellent. All right, so the first thing we need to do is to create a new study. Now, as I was just explaining when I noticed that there were some problems with the video, SolidWorks Simulation is an add-in to SolidWorks. So you can see I've got SolidWorks Simulation turned on here. It's available in SolidWorks Premium and also available as a separate package as well. So the first study that we're going to be running is a linear static analysis. This is available in the version of simulation that comes with SolidWorks Premium. The next two studies that we'll be performing, the fatigue study and the vibration study, are both available in the next tier up of SolidWorks Simulation. So it's available in what we call Simulation Professional. So I'm going to start a new static study here. Give it a name. And the first thing that we're going to take a look at is the materials. We can see we've already got material applied to these two components here, to the rod end ball and also to the pin, but the steering bracket itself doesn't have a material. So I'm going to apply a material to this part. We could use one of our standard out-of-the-box materials that comes with SolidWorks Simulation, but what I'm going to be looking at here is a custom material that I've created myself. The reason we're going to be using that is that it has a custom SN curve for use when performing fatigue analysis. So I'm going to apply that and close it. So you can see now we have 3 ticks down against each of the components there. All right. Next up, we need to have a look at how this is fixed to the test bench, as it were. So we want to fix this to a test bench so we can then apply a load to it and have a look at the stress. So I'm going to apply some fixtures. The first one is going to be a roller or slider to support the back of this, so it's allowing it to slide along. The next fixture that I'm going to apply is going to be a hinged fixture. So we're going to use that to simulate the support provided by the bolts. We can see that SolidWorks Simulation has a wide range of different types of fixtures to eliminate different rigid body motions of your individual components. Alright, so we've now held on to this particular assembly. The next thing that we want to do is apply a load to it, because without a load we're not going to develop any stress inside the part. So I'm going to apply a force. A typical steering force on this is going to be 6,000 newtons. So I'm going to select the face that I want to apply the force to, but I don't want to apply it normal to that face. It makes no sense to push in on that. So what I'm going to do instead is provide a selected direction. Now, a tip for those of you who are already using SolidWorks Simulation, if you pick a face, you then have to come down and activate whether you want it to be along the direction to, or normal to the plane. If instead for the direction you pick an edge, You only get one option, and it makes it much easier to supply the direction. So by picking that edge, I can then say I want it to be 6,000 newtons, reverse the direction, so we're applying it in the correct direction, and hit the tick. So we've now applied our fixtures, we've applied our loads. I'm going to use the standard out-of-the-box settings for the rest because we're not really focusing on the static analysis today. And I'm going to run this analysis. So this has returned my 3 standard plots. The first thing it tells us is that the maximum von Mises stress being developed in the part is 112 megapascals. So that's under the 150 that we had set as our goal. We can also see the areas where the stress is highest, and you can see there at the inside edges of this fillet through here, which is where we would expect to see the greatest amount of stress. Alright, so we know it's safe for a single load, but what we wanted to determine now is what happens over the life of the part as we load it and unload it up to 1 million times in this case. To simulate that, I'm going to create a new study. This is going to be my fatigue study, and we'll select fatigue. So what we have here, you'll notice that there are a number of different types of studies that I've got here. Now, with Simulation Standard, which is the level that comes with SolidWorks Premium, the only study that you get is the static analysis. When you move up to Simulation Professional, you gain the frequency, buckling, thermal, drop test, and fatigue, as well as pressure vessel design. Finally, when you move up to Simulation Premium, you gain the nonlinear and linear dynamic, as well as sub-modeling is also in the middle level, in the professional level as well. So we've got 2 options when it comes to applying or creating a fatigue study. The first is a constant amplitude event with defined cycles. So what that does is it allows us to load and unload the system using a known magnitude over and over again to a certain number of cycles. The second type, which is a variable amplitude history data, you need to supply a graph that over time defines the multiplication factor of the load that you want to apply. So you will provide a data that over the life you provide a graph that shows how you want to load and unload the system. In our case though, we're going to use a constant amplitude. Hit the tick. Now there's a few ways that we can apply this. When we come into the static study, there's not a lot in this static study here. If I right click, the only option I get is to add an event. With the constant amplitude, we have the option to set the number of cycles. In this case, that's going to be 1 million. Now, there's a few options in terms of how you want to apply it. Fully reversed, in our case, would basically mean the load applies 6,000 newtons in one direction and then applies 6,000 newtons back in the opposite direction, over and over again. Zero-based takes it from no load up to the 6,000 newtons and then back down to 0 again. You can also apply a loading ratio, so you can apply half the load in one direction and a full load in the other direction, or you can, if you've got a graph, you can find the cycle peaks and extract those out. In our case though, we're going to use the fully reversed option. Alright, so what this is talking about is we're going to be applying 6,000 newtons in one direction and then 6,000 newtons in the opposite direction, which makes sense because we're not only steering left in this rally car, we need to steer in both directions, so we want to apply 1 million loads in both directions. Okay? Next, we need to have a look at our materials. Now, if I select these 2 parts here and apply my material, we can see how the yield stress drops as you hit certain numbers of cycles of your of the loading. this is what we use to determine the effect of fatigue on your component. So I'm going to apply that. We've now got 3 ticks against our materials. We're ready to run. This study is very quick. As you can see there, we're finished already. And what we end up with is a damage plot and a life plot. So the damage plot shows that we have consumed in the area of maximum fatigue about 17% of the life of this component here. The other way that we can display it is the life plot. So this is showing how many cycles would we need to go through to actually consume all of the life in that particular area. And we can see here the lowest is just under 6 million cycles. So we can see from that we are definitely within our 1 million cycles that we're looking for. Now, there's a question that's come up. Somebody has asked about a sensor. So one of the things that we can do with a static study is set up sensors to let us know should we meet certain criteria. It doesn't just have to be simulation data, but it makes the most sense in this case here. To do that, I'm going to return back to the model and go to my sensors folder and add a sensor. If the sensors folder is not visible in your tree, you can go to your options feature manager and make sure that your sensors folder is set to show. But it is there by default. Right click, add sensor, simulation data. In this case we're interested in stress, von Mises stress, and I want it in megapascals, and I want to be alerted should it ever get greater than 150 megapascals. I hit the tick and I get a sensor added to my feature manager tree. Now should that alert ever get triggered, it will cause a rebuild error to occur, just like a normal rebuild error inside your assembly or part. A rebuild error will occur, and if you've got your what's wrong dialog box showing, then it will pop up your what's wrong dialog box and show you that this particular sensor has been triggered. Excuse me. So returning back to my study, if we run this again, the static study that is, we can see that it's showing that the stress is 112 megapascals, which reflects what we got here, and it hasn't been alerted because that value is under 150 megapascals. So we've satisfied our fatigue requirement here. What we'd like to do next is find out what the what the vibration is like in this system. So what we're most interested in is what will happen, or what will the vibrations of between 1 and 30 hertz be transmitted through this system as a natural frequency, and then via that through to the steering wheel and to the driver. So what we want to identify is what are the natural frequencies of this system. So what I'm going to do is create a new study. So a frequency study. Now I would like to bring in the material data and also the fixture data from one of my other studies, so from this static study. To do that, I can return back to my static study, grab the material data and just drag it with my left mouse button and drop it onto my vibration study. And if I come back into my vibration study, you can see it's now applied the material data to those parts. If I go back to my static study, I can also grab my fixtures, so my roller and fixed hinge, drag those and drop them again onto my vibration study, and it's copied those across. So now that I've got my fixtures and my material data, I'm able to run my vibration study. Alright, so what this is showing me here with my 5 displacement plots are the 5 lowest natural frequencies in the system. If I right-click on my results plot here, I can list my resonant frequencies, and I can see the lowest resonant frequency is well above 30 Hertz. So we're looking at 2,294 Hertz as the lowest natural frequency. So obviously if you had a motor or some other sort of recurring vibration inside the system, you can use a frequency analysis to determine if the vibration, the natural frequencies of your system coincide with any external forces that are occurring. And that way you can modify the geometry or the materials of your design to avoid that. In addition to that, we can actually animate these natural frequencies. So if I right-click on this first displacement plot here and animate it, we can see that that first first natural frequency is in this mode here. So moving it up and down. As we move to the higher frequencies, they become more complicated. So the next one is this side-to-side motion. Now we start moving into the twisting motions as well. So you can see for each natural frequency, you can actually see what the motion is that is occurring in those natural frequencies. Okay, so we're satisfied to ourselves that it is strong enough, that it is not going to fail due to fatigue within the expected life of the component, and that the natural frequencies are not going to coincide with the expected vibration that's going to be transmitted through the wheels and into the component. One other thing that we are able to do, though, is start to analyze the part for the purposes of where can I possibly remove weight from this. And this is where a design insight plot can come in very handy. So I'm just going to run my static analysis again here. And rather than the standard stress, displacement and strain plots here, I'm going to right click on my results folder and I'm going to define a design insight plot. What this gives me is a slider that allows me to show from the least loaded to the most loaded component, so or areas of this assembly. As I move it up, you can see that there's a big area through here that's not actually very loaded at all. So what this allows me to do is reduce the weight of the component without compromising the strength of the component. So what I'm able to do, I can leave this design insight plot active, and I'm going to create an assembly cut. So I'm not going to go into the part, I'm going to do it at the assembly level. So this allows me to play around a little bit in terms of removing material without actually affecting the parts directly. Once I've decided that the cut is something that I want to pass back through to the part, I could either copy the sketch into the part, or I could use some in-context design to copy the cut through. So I'm going to start a sketch on this back face here, and I'm just going to use some lines and arcs just to notch out this area here. I'm happy with that, so I'm now going to go to the assembly toolbar, assembly features, and create an extruded cut that passes just through the bracket area there. And we've removed that material from the part. I can now return back to my static study. It's giving me a warning. What's wrong? and the mesh information is not current because the model might have been updated. So to eliminate that, we need to rerun the study, which is going to remesh it and rerun the study. And I can see removing that area there has not increased the maximum von Mises stress in my components. We're still at 112 megapascals. So I've been able to use that design insight plot to identify areas that are not heavily loaded and remove that material and then rerun that study. I could also rerun my fatigue study and my vibration studies to make sure that it does not adversely affect either of those studies as well. All right, guys. Has anyone got any questions at the moment? So I'll get you just to use the question area to type any questions in that you'd like to see answered. All right, guys, I can't see any questions popping up at the moment. Ah, there we go. They're all coming through now. Yep, okay, so the first one there is the slider option of realistic fixture. So what it's providing there is support to prevent this face from moving. So along with most simulations, you're going to be taking some element of simplifying the support. If you wanted it to be more accurate, you could use something like a virtual wall. A virtual wall support would allow you to allow the part to pull away from the wall. It would also allow you to supply the friction or roughness coefficients between the back face of our component and the virtual wall. It may provide extra support or stiffness to the back component. So along with the studies that you perform, whenever I train simulation, this is never going to replace your real life analysis, your real life testing, but it's all about getting these tests, the FEA studies that you do, to be running as quickly as possible while being within the margin of error that you're looking to achieve. So you may find that the difference between setting up a virtual wall and just using the slider is, maybe 2 or 3%, and you're happy with that difference. You may also find that when you do these studies, that you find that there's a massive difference between the results that you get and that you don't have confidence in that slider support in this case. In that case, then you would need to use that virtual wall. So it's all about balancing the need for speed and the need for accuracy, and I can never state categorically, across all studies that you would ever set up, that one or the other is better. Now my screen hasn't hung, I just haven't been moving my mouse at all, so I'm still here. Okay, somebody's also asked about the contact conditions that we've got set up between the components. Again, in this case, I've used the default bonded condition. If you wanted to set up a no penetration contact condition, for example, between here, you could set that up. You would then also need to allow for the fact that this is able to rotate. You could eliminate that by possibly setting up a high level of friction between the components, or another level of support for this the rod end ball component here. The next question, somebody has asked where the SN curves have come from. Some of the materials in SolidWorks already have SN curves in them. So I'm in here, so if I go to static, you'll notice some of the materials already have an SN curve. So if I go into my SolidWorks materials here, some of these have got SN next to them, most do not. In which case you're going to need to get the materials data for that particular component, or sorry, that particular material yourself. Has anyone else got any other questions, or does anybody want any more clarification on the answers that I've given? Okay, somebody's asked about wind tunnel or fluid dynamics type studies. SolidWorks flow simulation is a separate package from the SolidWorks simulation packages, so that will allow you to do both internal and external flow studies on your components, but it's a separate package from SolidWorks simulation. Any last minute questions, guys? All right. Well, thank you very much for your time. I hope that you've got a lot out of it. You may receive a survey. Please fill that out and let us know both what you thought of this survey, of this webinar, and also if you've got any ideas for any further webinars that you would like to see. So if we've got no more questions, I'm going to close off this webinar and wish you all a great afternoon. Thank you very much.